This is the pre-post video that discusses the circumstance where we measure the same patients over time and that they have extreme values. Let's talk about what can go wrong when the patients within the groups being studied are extreme. For example, when we study those patients in a clinic that have the highest values of systolic blood pressure. It turns out that such patients will tend to become less extreme on remeasurement, even in the absence of intervention. The danger being that you might attribute the change in blood pressure, typically an improvement, to that intervention. Statistically, the cause of this phenomenon is measurement error. This slide lists some of the reasons that measurements of systolic blood pressure might change over time. Inconsistent readings from the measuring instrument certainly count as measurement error, but other factors that cause a patient's blood pressure to fluctuate, especially in the short term, are often included within the construct of measurement error as well. To understand why extreme patients tend to regress towards their means, we begin with the observation that in the absence of measurement error, really nothing's going to change. Put another way, the regression of y, the post-score, on x, the pre-score, will have a slope of 1. On the other hand, if measurement error is present, it can be shown that the regression coefficient beta will fall between 0 and 1. Moreover, the greater the measurement error, the greater will be the attenuation of this regression coefficient. One way to convince yourself that this is true is to imagine a really bad measuring instrument, one that performs so poorly that the blood pressure reading just entirely depends on chance. Accordingly, there'll be no relationship between observed blood pressures over time, and so the slope of the regression of y on x will be 0. Thus, with the most variable instrument possible, beta is 0, and with a perfect instrument, that is one with no noise whatsoever, beta is 1. The intermediate cases will fall between these two extremes. This table illustrates an intermediate case with beta equaling 1/2. Because of the impact of beta, extreme values of x truly do regress towards the population mean. Exactly the same phenomenon would hold for systolic blood pressure, with the example's mean of 0 being replaced with the average blood pressure of the population under study, and the values of the table shifted accordingly. Stated more systematically, extremely high values of x will tend to drop, and extremely low values of x will tend to rise. Moreover, the more extreme the value of x, the greater will be the amount of change on remeasurement. Well, exactly why does regression to the mean occur? It turns out that, for example, patients with extremely high readings on systolic blood pressure will tend to have moderately high true blood pressures and positive measurement error. Since the positive measurement error is unlikely to be repeated at time 2, what you'll see at time 2 is just the moderately high true blood pressures. This table contains an IQ example that illustrates why patients with high observed ratings tend to have high positive measurement error. Most patients in the example have true IQs near the population average of 100. Smaller yet still notable number of patients have true IQs near 120. Fewer still have IQs near 140. IQs near 160 are extremely rare, and so forth. Going across the rows, the observed IQs are as predicted, centered around their true values. Please note that the table doesn't show the 10,000 people in the first row with observed IQs of 80. But now look down the column at the observed values of 120. Although some people with that observed value do have true values of 120, just about as many have true values of 100, just happen to get lucky on the day of testing. Almost no one with an observed IQ of 120 has a true IQ of 140, mostly because there are so few people with true IQs of 140 in the first place. The same phenomenon occurs regardless of column. It should also be clear for the construction of the table that the more the variation within the row, that is, the larger the measurement error, the more dramatic will be the phenomenon of regression towards the mean. This table also illustrates why regression to the mean can be so counterintuitive. People with high recorded IQs actually are smarter than average, they're just not as smart as they appear. And of course, the same phenomenon occurs for systolic blood pressure. For pre-post designs without controls, the implication of regression to the mean can be dire. You'll not only overestimate the average effect of interventions, you'll wrongly conclude that the intervention has the strongest impact in the patients at highest risk. This is great if you're selling quality improvement interventions. Just sell them to the most desperate clients with the biggest apparent quality problems and rely on regression of the mean to make their performance appear to improve. It's unfortunate for everyone else, though. Really, the only solution is to use a randomized control group. Then both groups will be expected to suffer from regression to the mean in equal magnitude. With intervention versus control as the primary variable of interest and pre-score as the covariate, what you have is an ANCOVA model covered in other modules.